And the first talk of the semester will be by David Eppstein from UC Irvine. And he's going to talk about the topic which apparently, am I correct, won the best paper award at SOSA?
Yes.
Maybe you could explain what that is. And I tried to reconstruct like if David actually spoke or attended this seminar hundreds of years ago, and I failed to reconstruct this. I'm sure it was the case at some point, but
I did attend this seminar in the late 80s. So yes, long ago.
20th century?
Yes.
Well, that answers the question. So I would stop interfering and let David speak.
This is research that I did at a couple of these virtual online research workshops that have replaced the in-person workshops we used to have in Barbados. And so I'm thankful that that is still going, but I presented this at the Symposium on Simplicity in Algorithms, part of SOTA this January, and it won the best paper award there. So finding relevant points for nearest neighbor classification. Let me start by telling you what that is. So as background, there's a lot of work in this direction that this is a small piece of, but it comes from a problem in supervised learning. So supervised learning means that you've already seen data that you know how it should be classified. And based on that information of known classifications of data points, you want to be able to predict the classifications of points with unknown classifications. So given these points that are somehow classified as either being blue circles or red squares, you get this new point, doesn't come with a classification attached to it. You need to decide on its classification. This could be an online version where after you've determined the classification, you learn what its true classification is and update your learning system. Or the setting that I have in mind is more just a static one where you have a static training set. You have to build the best classifier you can, and now you use it to classify a lot of data. So nearest neighbor classification is a very standard way of doing that. Useful when you don't know a lot more about the data beyond just some kind of distance structure. Maybe these are points in some Euclidean space, and that's the setting that I'm going to be looking at, where you're just going to guess that your new point has the same classification as the nearest existing point. So in this case, the new unknown point that I showed in the figure, its nearest known point is one of these red squares. And so you're going to guess that's probably another red square. There are other ways of doing this. Simple ones based on nearest neighbors. For instance, you can look at several nearest neighbors and look at the majority classification among those. You can use more complicated processes to try to learn smooth decision boundaries between the points. But I'm going to focus here on nearest neighbor classification, the simplest of these classification systems. And this has led to an enormous amount of work in computational geometry on just what are the boundaries between these decision regions of nearest neighbor classification. So given these red points and blue points, now they're in a grid, but it's still points with two classifications. They divide up space into regions where the classifications differ. And those regions are essentially just unions of cells of a Voronoi diagram. So we all know about Voronoi diagrams. You partition Euclidean space or some other space into cells. The cells have each of these training points as nearest neighbors. So within this entire violet cell, this central point here is the nearest training point and the one that would be used for nearest neighbor classification. And then the decision boundaries from this previous figure, the boundaries between different classifications are boundaries between cells of the Voronoi diagram, but they're not all of the boundaries between cells of the Voronoi diagram. They're boundaries between cells that have different classifications. For the two-dimensional Voronoi diagram, there's again been an enormous line of research on point location data structures, which allow this problem to be solved in n log n pre-processing time, log n query time to classify each unknown point. There are better point location data structures known for situations where points are well within their cell. It's a pretty well-studied and known problem. In higher dimensions, and higher dimensions are really what I'm interested in this talk, the Voronoi diagram works in the sense that it gives you the correct decision boundaries. But there's this curse of dimensionality going on here where the combinatorial complexity of this Voronoi diagram and of constructing the Voronoi diagram and using it to perform classifications grows pretty badly in terms of the dimension and the power of dimension over 2. So even in 3 dimensions, you've gone up from n to n squared complexity to construct this Voronoi diagram. By the time you get up to 5 dimensions, it's n cubed, et cetera, et cetera. It works, but not very efficiently. And so there, again, another line of research that people have looked at, instead of doing the obvious exact sequential search where you don't use any data structure, you just look through all the points and check which one is the nearest. It takes linear space and linear query time. Maybe you can do something approximate. I've listed one of my papers here as an approximate nearest neighbor data structure, but there are a lot of them. In spaces of bounded dimension, we can get a nearly exact approximate nearest neighbor, a neighbor that is within 1 plus epsilon distance of the true nearest neighbor. In, again, log n query time, linear space, but there is still a dependence on the dimension here hidden in this time bound that is exponential. Or in larger dimension, you can use these locality-sensitive hashing techniques, which work for spaces of arbitrarily large dimension and give you slightly superlinear space and slightly sublinear query time, depending on how accurate you want your results to be. But slightly superlinear space and slightly sublinear query time are only slightly better than the linear space and linear query time that you would get from just sequential search with no data structures. So there are a lot of things that we can do that do a little better than just naive sequential search, but not a lot better. And what I want to talk about today is something that you can do kind of independently of all of those techniques that works regardless of what structure you're using to do your nearest neighbor queries. And that is to, instead of using your original data set of training points, to somehow slim it down to a smaller training set of fewer points. And so maybe there's some way of not using the whole query set to use only some smaller subset of it in a way that hopefully doesn't make your classification accuracy worse. You're getting the same results, just fewer points. So the way I'm going to do this is through a notion of the relevant points of a data set. And a point is irrelevant like this X'd out red point in the corner here. What I mean by that is it's a point that can be removed without changing any of the decision boundaries. Another way of saying that is that for all of the points in its Voronoi cell, the second nearest neighbor, the point that would become the nearest neighbor if you remove this point, has the same classification as the removed point. And so if you remove this point, it doesn't affect the nearest neighbor classifier algorithm. That'll just move on to this other nearby point with the same classification and produce the same prediction. It'll use a different neighbor to produce that prediction, but the prediction itself will be the same. And so if we can do that, that point is irrelevant. And what I want to do is to find the subset of points that are not irrelevant, the relevant points. The reason for finding that whole subset is rather than just removing one point at a time, you can actually remove all of the relevant points simultaneously, and it still won't affect the decision boundary. Because every piece of decision boundary is a wall between two Voronoi cells of different classifications. And those 2 points defining that Voronoi wall are necessarily themselves relevant. They cannot be removed in this removal simultaneously of all of the irrelevant points. And so after you remove all of the irrelevant points, those walls will still be there in the same places that they were before. And here I have an example. It's a one-dimensional example now. The relevant points here are the ones that are on a boundary between 2 colors of points. And if we keep only those points and throw away all of the other same color points between 2 of them, we get the same walls and the same decision classification. So that's the problem that this paper solves. We're given a set of training points in some Euclidean space of some dimension. These points come with coordinates, but they also come with classifications. That's what it means to be training points. And given these classified points, I want to find all of the relevant points. The time bounds that I'm looking for are output sensitive time bounds. And what I mean by that is that they're going to depend on the number of relevant points that remain. So if I have a large number of training points, but only a small number of relevant points, I want the algorithm to be faster. And as you can see from this picture, I'm going to allow more than 2 classifications of points. You could consider this problem as a binary classification problem, yes or no, true or false, but the same techniques turn out to work for non-binary classifications. And as you can tell from this earlier picture, I also don't want to assume anything about the points being in general position. These points are not in general position. They're on a grid. There are decision boundaries here where in this 2-dimensional example, 4 boundaries meet at a point that would not be possible for general position subsets of points. And so I want to be able to find this kind of decision boundary as easily as any other decision boundary. So that is the problem that I'm going to be solving. Now let's start by looking. This is an algorithm that's not from my paper. It's really something that was previously known, but I wanted to start with a simple warm-up problem. The warm-up problem is to solve this relevant point problem in 1 dimension. And so we want to find all of the points that have a neighbor that is a different color from them in this sorted order of the points, because those are the ones that are relevant. They're the ones that define a decision boundary. And so one algorithm for this is just to sort all of the training points. And once you've sorted them, you can look for each point. Is it next to, immediately preceding, or immediately succeeding a point with a different classification? If so, keep it, otherwise throw it away. The main step of this algorithm is just sorting. So in a comparison sorting model, it takes n log n time. If your points have integer coordinates, you can do faster. But we can actually do better and get an output sensitive algorithm for this same problem. And there's a very simple way of doing that, which is just that we use quicksort. But when we're using quicksort, you remember quicksort will randomly pick a pivot point, say this red one, divide the remaining points into the points below and above the pivot, and recurse. Randomly pick a pivot, say this blue point on the left side, divide into below and above, and recurse. But when that recursion, when a recursive subproblem ends up having all of its points with the same classification, which we can check in time proportional to the size of the subproblem just by checking all the classifications, then we don't need to recursively sort that subproblem. We can stop and find the minimum and maximum of that subproblem. And if you do a little analysis of the expected number of comparisons that any item in this whole input participates in, that expected number of comparisons turns out to be a logarithm of something depending on how far it is from the nearest decision boundary. And when you add that up over all of the input points and find where the decision boundaries would be to make that sum as large as possible, it turns out to be n log r. So very simple modification of quicksort. Just like quick select only recurses down into the subproblem containing the median, this is a variation of quicksort that only recurses down as far as it needs to in order to find these blocks of points that are all the same color. The blocks that it stops recursing in are not the same as the contiguous blocks in the sorted input. They're subsequences of it, but that's enough to get a fast algorithm, n log r instead of n log n. So that algorithm was known, actually. In fact, you can get n log r deterministic running time using medians as your pivots instead of just using random pivots. That was known from a paper by another of these workshop papers. So it's got like 8 authors, starting with Bremner in a CCCG 2005 paper. But the main result of that 2005 paper was that you can get that same n log r output sensitive running time in 2 dimensions, where in 2 dimensions, the obvious n log n algorithm is compute the Voronoi diagram, choose the points that have a Voronoi neighbor of a different color, output them. That takes n log n time. You can reduce that to n log r, just as you can in this 1-dimensional early stopping quicksort algorithm. Now, in higher dimensions, there is an algorithm known for this relevant point problem from a paper by Ken Clarkson from Fox 94. The running time depends on the dimension because there's some linear programming hidden in here. But the time is either you can get n cubed time, just straight up n cubed, not output sensitive, but no logs. Or if you're willing to pay a log n factor, you can get an output sensitive algorithm that turns that one of those n's into an r. And so that was what was known until my new paper. And what I'm going to prove is instead you can get an algorithm that still kind of has this cubic behavior, but 2 of the n's have turned into r's and there are no logs. So running time order n squared plus r squared n. There's an n squared overhead that doesn't depend on r that I don't know how to get rid of, and then an r squared n term. That's in any constant dimension. In a dimension that's not constant, the algorithm still works, but its running time is going to depend on the time for linear programming. And in a very small dimension, like 3, 4, or 5, we can get these much messier time bounds. So roughly n to the 4/3 in 3 dimensions. Something worse than that, more like n to the 5/3 in this side. But in 4 dimensions, but the n part is still n to the 4/3. And there's this kind of every other step here where there's 2 parts to the time bound, just like there are up here, a part that depends on n and a part that depends on r. The part that depends on n goes up in the odd dimensions, and the part that depends on r goes up in the even dimensions. And really what's going on with these time bounds, and I'll get into that in a minute in more detail, is the n squared, n log n to the 4/3, n to the 4/3, n to the 3/2. That part of the running time is how much time it takes to find a minimum spanning tree. And the part that depends on R involves finding the vertices of convex hulls of sets of points. So the extreme point problem. Now this paper was in SOSA, the Symposium on Simplicity in Algorithms, and time bounds like the ones down here don't look like very simple algorithms. And they're not. But these time bounds up here are. So in any fixed dimension, it turns out there are known algorithms for finding the extreme points in a simple and implementable way based on low dimensional linear programming, which is also pretty simple. And then the Euclidean minimum spanning tree is even simpler if all you want is an n squared time bound. So we want to be able to find all the relevant points, and we're going to use these 2 ideas as subroutines. Okay. So let's look at the algorithm for this. And the algorithm has 2 steps, one involving minimum spanning trees and one involving extreme points. First step, compute the minimum spanning tree of the whole training set. And what I mean by that is just form a complete graph that has the distances between the training set points as the weights. So the construction of the minimum spanning tree doesn't depend on the classifications. But then once you've constructed it, look at the endpoints of edges in the minimum spanning tree that connect pairs of points with a different classification from each other. Here I've got some edges connecting a red point and a blue point and a yellow point, a red point and a blue point, a yellow point and a blue point. Those points have different classifications from each other, and so those edges define 2 relevant points. I'm going to identify both endpoints of those edges as being relevant. And the intuition here is we're not going to find all of the relevant points and all of the decision boundaries this way, but we're going to find a little piece of each one. And once we've done that, we need to grow these decision boundaries so that we get all of them. And that's accomplished by the second step of the algorithm. So once I find a point P as being relevant, I'm going to look at the set of all of the points that are different in classification from P. Ignore the points that are the same classification as P, just take the ones that are different and invert them all through a circle centered at P, or a sphere. The radius of inversion turns out not to be relevant, so you might as well assume that it's a unit sphere centered at P. And what I mean by inverting is just each of these differently classified points gets moved on its ray. If it was outside the unit sphere, it gets moved inside. If it was inside the unit sphere, it gets outside, to a point where the product of these two distances, the inside distance and the outside distance of that point along that ray and its inverted image, that product of distances should equal 1. So take all of these differently classified points, invert them. That's just a simple calculation. Add this point P that we found as relevant to this set of inverted points. One more point added to the set of inverted points. And find the set of extreme points of that inverted point set, the set of vertices of the convex hull of that point set. And I'm going to declare as part of the algorithm that all of those points that we find in this step are relevant. And so we start out identifying relevant points from the minimum spanning tree and then performing this algorithm of inverting and extreme points on those relevant points. But once we find more relevant points through this inversion and extreme point process, those ones will be plugged back in, and we do the same thing with them again. And once we find a relevant point in this process, we use it as the center of a new inversion and a new extreme point calculation. So we do one of these extreme point calculations for every relevant point that we find. Okay, let's start with the minimum spanning tree step. This is all pretty standard. In 2D, the edges of the minimum spanning tree are a subset of the pairs of points that are adjacent in the Voronoi diagram, or if you prefer, the edges of the Delaunay triangulation. We can construct the Voronoi diagram in n log n time. Its set of adjacent cells forms a planar graph. We can find the minimum spanning tree of planar graphs in linear time. And this gives us the Euclidean minimum spanning tree of any set of points in the plane. This was known in the 70s. In higher dimensions, the time for Euclidean minimum spanning trees is this mess. And it involves transforming the problem into one of finding bichromatic closest pairs. There's a time-preserving transformation between those two. They're essentially equivalent in complexity. And then using range searching. And you get a time bound that looks like this in any constant dimension greater than 2. In dimension 3, it's n log n to the power 4/3 without the epsilon. And that's all in this paper from 91. I don't think there's been any progress on the problem since then, really. On the other hand, if you're looking for a simple algorithm that only gets you an n squared time bound, it's much, much easier. There's a lot of different algorithms that can compute minimum spanning trees in n squared time on complete graphs. One of them is just Yarnik's algorithm, where we build a tree from an arbitrary starting vertex, one edge at a time, using a priority queue. Only we implement this algorithm without the priority queue. Instead of using a priority queue to find each new addition to the minimum spanning tree, we just do a sequential search. So create triples of points, and the best connection we found for each point outside the tree to something that is in the tree, initially infinity, that's the priority in the priority queue. And then repeatedly pull out the minimum priority point by doing a scan of this entire list rather than doing any data structures. Remove that point from the list and update everybody else's priority. And that takes linear time per point or n squared time overall. The minimum spanning tree consists of the pairs that you found in this way. So standard graph algorithms applied to the complete graph in n squared time. Now the extreme point problem, again in 2D, it's just a set of vertices of the convex hull. Another way of thinking of these is that they are the maxima of some linear function on the input points. So for each vertex of the convex hull, like this one marked here, there is some linear function, this green function that increases upwards and to the right, that for which that point has a larger value than all of the other points of the input set. And that defines it as being an extreme point. If I had, in this example, if I had a point lying on the edge of the convex hull, that would not be an extreme point. I only want the vertices. And so for dimensions 2 and 3, we know how to compute convex hulls in an output sensitive way. And that's going to be relevant for our time bounds because output sensitive construction of extreme points is going to turn into output sensitive construction of relevant points. If there are k extreme points, they take time n log k. In dimensions greater than 3, you can identify the extreme points in, again, this messy time bound that depends in some way on the parity of the dimension, but is slightly subquadratic in large but constant dimensions. On the other hand, there's actually a known simple subroutine for finding the extreme points of a data set. If I want to find all of the extreme points of a set of n points, well, there's a simple n squared algorithm that's maybe kind of obvious, which is for every given point, you can solve a bounded dimension linear programming to test whether it's extreme. And if you do that in linear time per point, that's n squared overall, but you can do better than that. So let's initialize the set of extreme points to be the empty set. And then for every input point P in an arbitrary order, I want to do some computation that either adds one to the set of extreme points or determines that P is not extreme. And so what I'm going to do is use linear programming to search for a vector that shows that P is more extreme than the set of points we've already identified in the direction of that vector. In other words, let's test if P plus E, if in that set of points that we've found so far, plus P, is P one of the convex hull vertices of just that subset? It's a linear programming. You can solve it in time O of K because it's a bounded dimension linear program with order K constraints. Now, once we've found this vector, it might not be the case that P is actually extreme for the whole input. But we know that whatever vector is the farthest in the direction of V, the most extreme point for that direction that we found, that point really is extreme for the whole input set. So if we find a vector showing that P is extreme in the set E union P, then that helps us to find another point that's extreme for the whole input set in time proportional to the number of extreme points. And if we find that point Q, then we go back and test P again and test P again until either P itself gets added to the set of extreme points, or we can determine that it's not extreme. Every time through these loops takes order K time because we're doing a linear program. We do that once per point, and so the total time is O of Kn. And so we can plug in and get our overall time analysis. Just add together the times for the minimum spanning tree and the extreme point computations, producing n squared plus r squared n simple algorithm, or these messier complicated algorithms, or in unbounded dimensions, we get a time bound that basically consists of nr linear programs, each having r constraints, and whatever the time bound for that is. It might seem like I'm done here because I've described an algorithm and given the time analysis and what more is there to do, but I'm not done, because describing the algorithm and analyzing its running time is actually all straightforward. The hard part of this result is understanding why minimum spanning trees and extreme points combine in this way to find all of the relevant points. Why does it work? It's not obvious. And the proof is messier than any of the stuff that I've gone through before. So I'll go over it, maybe not in full detail. First, I mean, there's really two things that we have to check. We need to make sure that all of the points that we find are relevant, and we need to make sure that we find all of the relevant points. And for the first step of the algorithm, this question of, are all of the points that we find relevant? Actually, that's pretty easy. Every time we have a bichromatic edge of the minimum spanning tree, that edge, it turns out, pierces the Voronoi wall between those two points. So not only does that edge of the minimum spanning tree, not only is it dual to a wall between two Voronoi cells, but it actually pierces that wall. That's not true for other Delaunay edges, but it is true for the minimum spanning tree edges. And so that midpoint of the edge is a point where these 2 points of different colors are the unique closest 2 points to that midpoint. If we removed either one of these midpoints, either one of these two endpoints of the minimum spanning tree edge from our training set, the classification would change for points in its cell near that midpoint. And because the classification would change, that is a relevant point. So all of these points that we find here are relevant. It's a little trickier to argue why the extreme points that we find in the other step are relevant. Really what I'm doing when I'm finding extreme points in inverted sets is I'm finding the Voronoi neighbors. This blue point is the point that I'm inverting around in this picture. I've inverted all of the red and yellow points with respect to that blue point and found the extreme points of that inverted set. Really, if you work through the geometry of what that means, it's just that we're finding the Voronoi neighbors of the blue point. In extreme points of this inverted set are nothing more than the Voronoi neighbors. So that's all we're doing in that calculation. But they are the Voronoi neighbors. They're not the Voronoi neighbors in our full training set. They're the Voronoi neighbors in this weird subset of points where we've got this one point, the relevant point, that the center of the inversion with one classification and a bunch of points that have a different classification from it. And so each of these points that we find as a Voronoi neighbor of this blue point looks like it's relevant for that subset of points. So this red point up here, the midpoint of its Delaunay edge between that point and the blue point, that midpoint actually pierces the Voronoi boundary, and both of these points are relevant near that midpoint for this subset of points. For this other red point I've highlighted over here, you can't actually see the Voronoi diagram that it's relevant for in this picture. It's off to the left somewhere. It's hidden by this other Voronoi diagram of this other red point. But there is a Voronoi diagram somewhere out here, and it's not pierced by this edge, but that's irrelevant. There's still a point somewhere in the middle of that Voronoi wall between those 2 points, for which in that subset of points, it's a relevant point. But it's not a relevant point for the whole training set. And the reason for that is there's all these other blue points out here. If I look at the point where these 2 points are the nearest neighbors in the training set, then it has a lot of other blue points that are nearer to it, but it doesn't have any red or yellow points that are nearer to it. That point on the Voronoi wall does have this shaded red point as its nearest other color point. And so if you traverse a line segment from that Voronoi wall directly to this shaded extreme point, that line segment starts out in a blue boundary, in a blue decision area, and eventually crosses a decision boundary into the red decision area. As it does so, this red point remains its nearest point. And so at the point where it finally crosses between the red and the blue decision boundaries, which is probably somewhere around here, this point becomes relevant. And so it is a relevant point. All of the points that we find are relevant, but it takes a slightly tricky argument. So final argument involves the completeness here. We still need to show that all of the relevant points are identified, not just some of them. We've shown that the points that we find are relevant, but we need to show that all the relevant points are going to be found. And so to do that, I need to somehow pick out pieces of boundary and make a separate argument for each piece of boundary. And the pieces of boundary that I'm going to consider are defined in kind of a complicated way. So if you look at a subset of Voronoi cells that all have the same classification as each other, this blue subset here, you can divide those into connected components of cells that are adjacent to each other across Voronoi walls. And in this case, there are two blue components, B1 and B2. B1 has a boundary. That boundary is shown as the solid black edges. B2 has a different boundary that's just the square around that one cell. Now looking at the boundary of component B1, that boundary of component B1 itself can be divided into components. I haven't highlighted it here, but there's actually another piece of boundary of B1 separating B1 from R3 in the middle here. And that's a separate component of boundary from the boundary that I've highlighted in black. So you take subsets of Voronoi cells, you take their components of cells with the same classification, you take the boundary of a component, and then you look at the components of boundaries. Those are sets of Voronoi walls that are adjacent to each other across D-2 dimensional things. In this picture, that just means vertices. In 3 dimensions, we would have a set of 2-dimensional walls adjacent to each other across Voronoi edges and so on. The reason for doing things in this complicated way is then we can use homology. According to the theory of homology, the boundary of any shape is the set of next dimension down things that are touched an odd number of times because I'm using mod 2 homology. And boundaries of boundaries are always empty. What we're looking at is boundaries of components of boundary. So the boundary of this black, solid black component of boundary is an empty thing because it's a boundary of a boundary, or it's a component of a boundary, but taking components doesn't separate it, doesn't change this touching an even number of times thing. Because this solid black line is something with an empty boundary, that means that it is itself a boundary of something. We defined it as a component of boundary of a decision region, this blue region B1, and it is that, but it's also itself a boundary of something. It is the boundary of B1 union R3. That is a subset of cells that doesn't make sense for classification purposes, but it does make sense to show that this component of boundaries is a boundary of a set of cells. And because it's a boundary of B1 union R3, the minimum spanning tree has to cross that boundary. Somehow the minimum spanning tree has to connect from the stuff outside B1 union R3 to the stuff inside B1 union R3. And when it does so, it crosses this boundary and it finds a pair of relevant points on one of these Voronoi walls that was part of this solid black component of the boundary of B1. And that's true for every component of boundary of something. So our minimum spanning tree phase of our algorithm will find a pair of relevant points determining at least one wall in every component of boundary. Once they do that, once we find just one of these walls in this component of boundary, then there's another geometric argument that goes on to show that when you look at the extreme points of inverted points of one of these relevant points of one of these walls, it's going to find a bunch of other relevant points that might not even be part of the same component, but among those, it will find the neighbors in this component of boundary. And so you'll find the neighbors, you'll find the neighbors of neighbors, and you'll expand out to find the whole component. So the minimum spanning tree finds a piece of every component of boundary. The extreme point part of the algorithm expands that out to the whole component. And so we eventually find every relevant point. Okay, that's pretty much everything I had to say. So we have a simple algorithm for relevant points in any dimension. It works best when there are many fewer relevant points than the size of the whole training set, because it is faster than previous algorithms by replacing n by r in its time bounds, and that works better when n is much bigger than r. When the dimension is a constant, you get a linear time, linear programming algorithm and an r squared n plus n squared overall time bound. The same algorithm works even when that's not true. If the dimension is unbounded, you can just plug in any linear programming algorithm. You can plug in any minimum spanning tree algorithm or extreme point algorithm in low dimensions, and we did not need to assume general position. There's a lot of ways I could take this further that I have not yet done. It's simple, it looks implementable. I have not implemented it. I did implement the quicksort algorithm with the early stopping, but not anything else. It would be nice to know what we can expect R to be as a function of n and the dimension. What is the typical growth rate of this number R for typical data sets? Does this really help? Is it a useful thing to do, or are most of the points relevant already and you don't trim much? It's not always the case that the relevant points are the smallest subset that give you the same decision boundary. Sometimes if you remove other points that are relevant, you can get a smaller subset with the same decision boundary. And that looks like a much harder problem. So there's some interesting algorithmic questions there. And then an obvious question that was asked at my SOZA talk is, what can you say about K nearest neighbor classification? I don't know, but I think it's interesting. So I will stop there and take questions.